Ladies and gentlemen, Jim Tauby.
Thank you. Thank you for having me here. All right. Being a New Yorker, I don't need to have a microphone. We speak very loud in New York, so I'm used to talking to groups like this. All right. So basically what I want to go over today is restraining of building services. That would be your mechanical, your electrical, your fire protection services within the buildings, all right, from both seismic and blast. All right. Unfortunately, your city and my city are two of the biggest targets in the world for terrorist activity. All right. So what we have is most of the stuff that we're going to be going over today, it came out of the ASHRAE manual, A Practical Guide to Seismic Restraint. In there, we have one complete chapter on bomb blast protection. All right. It's a topic that we've always felt was needed. So we've added it into it. Like I said, it was coming out of this. This is the second edition. The first edition was in 1998, and it was published by ASHRAE. It is one of ASHRAE's largest selling publications. Right? It averages somewhere around 2,000 copies a year get bought of this manual. Right? ASHRAE is now, this manual here, the actual picture I got is got a little different than the front cover of the newest edition, the next version of it. It's ICC approved, which means as part of the United States Building Code. This is now part of the building code in the United States. It says in there that if you want to do seismic work, this is a recommended method of doing your seismic work, right? In New Zealand, it actually says we want you to use this as your method of design for seismic restraints for your mechanical systems. Okay. So probably one of the most important things to get across is specifications. Okay. It's probably the most important way to make sure that a project is constructed as you have perceived it in your mind. All right. It requires a properly prepared set of drawings, construction documents, both drawings and specs, detailed review, approval, and then the ultimate part, field enforcement. And you would not believe how many job sites I go to. We do a lot of work with the U.S. government on U.S. embassies, and I have to go to these embassies and actually inspect them. You'll give them exactly what you want. You'll hand them the parts to put in. You'll hand them the bolts, and they won't put them in. They'll, oh, that bolt was too big. I didn't want to drill it into the concrete, so I got a smaller bolt and put it in. Or your bolt was too long. I cut it in half. All right. Field enforcement is one of the main problems that we have in the industry. People are just like, their mindset is, I've been doing this for 40 years. We've never had an earthquake that has had major damage. I know what I'm doing, and they just change what your design to whatever they want to do at that particular moment. All right. Seismic and bomb blast has to be looked at as an engineered system. Not that you can just open up a catalog of some company and say, give me 5 of this, 6 of that, and 7 of that, because you have to first figure out what your loads are. What are your blast loads or what are your seismic loads on every piece of equipment? And then from there, you have to select what you need to hold that in place. All right. You have to look at the complete load path. And that is the equipment down through the bolting, any anchorage into the structure itself. And that includes, okay, what we call housekeeping pads, but I think you guys call them plinths here, correct? All right. And people go, what do I care about a plinth? It's probably the most important thing in anything we talk about tonight, because I'm going to show you some extreme photographs of what happens if you don't design a housekeeping plinth correctly. So when you have a blast, when you have some kind of explosive blast, all right, in an earthquake, the floor starts to move, okay? In a blast, what happens is the building starts to move because you've got an air wave that is hitting the building from some distance away. If it's inside your building, that's totally different, but most blasts, and what we're going to be looking at is if it's out there, what happens to the building as it comes this way, as the blast comes this way, right? So what you've got is a standoff distance and an air blast, okay? Now, in most places, the building itself can handle whatever the blast is, but it's your windows and doors that don't really handle it well, and that's when the blast comes into the building itself. All right, so that's when the airways and the shock waves make it into the building. It's through places such as that. Okay, with the ground, whereas the ground acts like an earthquake, it is dependent on the mass of the equipment, and air blast damage is more based on equipment surface area, because you've got, just like a wind force, you've got a certain amount of physical space coming at the equipment, or the piping, your ductwork, your electrical services. So it's really like a wind load coming at it, but not any wind that you've ever seen. All right, it comes out at hundreds of miles an hour. The structure responds to the loads imposed on the air ground and the ground shock. There will be a shock in the ground also. So there will be a minor earthquake in any blast, right? Just because the ground is going to move, because some of the ground will move just like it is an earthquake, because you're actually making the ground move, all right? You can end up with fairly large accelerations, all right? And space and large displacements end up being quite common. All right, so you look at some of these equipment in here, and what happens is the equipment starts to want to move back and forth, right? Or actually more in one direction than it is in the other directions, right? So what you're trying to do is make this stuff survive, right? So what you're trying to do is make all of this survive what happens in the air blast itself or in an earthquake, right? The equipment is stupid. It doesn't know the difference between an air blast and an earthquake. It just knows that either something's pushing on it or the ground underneath it is trying to move away from where it is, right? And so what you're doing is a lot of the bomb blast work is almost identical to what we're doing for seismic work. You're bracing stuff to stay in place, or you're designing the anchorage to limit the movements, one or the other. Okay, blast loads can enter the buildings through utility openings also, all right? Explosions produce primary and secondary fragments, all right? Your primary fragments are from the explosive device. The secondary fragments are from the building itself. That's your concrete in the building, the glass in the building. In other words, new shrapnel from that blast moving on, continuing on with the blast as it goes. All right, so you have to look at both those things. All right, the equipment can see very large accelerations. All right, a typical large blast can move equipment halfway across the room. All right, or if the room is still there after the blast. All right. The equipment must be able to survive these accelerations. That is if you want to make sure that the building is usable, right? In the United States, what we do is we have two criteria for buildings. We have what we call a standard commercial building, which would be something like this, right? And they have one set of criteria. And then you have places such as, come on in. Come on in. So what you have is, the second place is, where was I? Let's find these accelerations. I lost where I was now. What was I just saying?
Two criteria.
I'm sorry?
You said there were two criteria.
What was the first one?
Yeah.
What was my first criteria?
It's got to survive the acceleration.
I'm sorry?
It's got to survive the acceleration.
Oh, okay. Got to survive the acceleration first. All right. And the second is they basically have to, the second one is we have hospitals, police stations, fire stations, places like that, that you want up and running after any kind of event. All right, those are your places that must be open. All right, so in the United States, we have a different code, not a different code, we have a different importancy factor that we put on for that. And basically it's, if your standard commercial building is designed, we'll say for 1G, these are designed for 1.5 to 2 Gs. So they're basically for twice the force of the basic earthquake in the area. Okay? What happens is you have to take a look at equipment fragility levels. In other words, when this blast or the earthquake comes, how is this piece of equipment going to handle? How is it going to survive? All right? Pieces of equipment such as a pump are very good. I mean, it's just a block of steel with an impeller inside. They're very good. They have very good fragility levels. You take an exhaust fan, well, that's a little different. That's a sheet metal box with a fan inside, and that usually doesn't have as good of a fragility level just because it's easier to come apart, easier to be thrown out of alignment, okay? So what we have is, yes, sir?
It's not the term we have here, the TM5, what are they're not?
Those are U.S. government military documents.
Okay.
All right, they're,
Okay.
basically what they are is the government has different documents for different pieces of equipment, and some of this is also being done by, what used to be done by our nuclear agencies. They used to have fragility levels on equipment, but since we haven't built a nuclear facility in 40 years in the United States, it's kind of lost its peak, okay? So it all depends on where you're going to get it from, but some of them, like centrifugal fans, 15 to 20, all right? Pumps, 6 to 10, but then this document says 15 to 45. So it all depends on what document you want to use, but they're different documents. They basically come out with different answers, but the basic answer is they're fairly stout in most cases. Okay, here's one that didn't do so well. Now, this is a photograph. All these photographs that you see are in the ASHRAE book, right? We have a whole chapter just on photographs of things that did well and things that didn't do so well. This is one that didn't do so well, right? So basically, this is a cooling tower, and this cooling tower has bent sheet metal legs as channels, all right? And they took care of the vertical load perfectly. But once there was some horizontal load added to them, this corner just buckled and down came the rest of the cooling tower, all right? In the United States now, the building official has the right to ask for a certificate of compliance to show that a piece of equipment that you're going to put on his job can meet the seismic requirements of that area, okay? Basically, it's done in California on hospitals, though. You don't see many other places asking for it, but you do run into it now and again. And most companies in America now are shaker table testing all of their equipment to see what they get as seismic capabilities of the equipment, all right? Mason Industries, my company, does a little bit of overseeing some of this work for different companies, and will be there while they actually run the tests, and will supply equipment for it. And you would not believe how many of them, they'll start out, they'll think it's great, something will fail, they got to go back real quick, figure out what to do, fix it, and then start the tests over again, okay? All right, there are two ways to analyze HVAC equipment, all right, for seismic and bomb blast. There's the static analysis. That is just code-driven calculations. And that is what 90% of the work is done that way. In other words, you take a pump, it weighs X amount, it is mounted this high off the ground, it's this wide, and it's just mathematics. A force coming in, overturning, and you work out what your loads are going to be, and you end up with figuring out what kind of anchorage you need, okay? The other is a dynamic analysis, right? That's where you basically do the same thing, but you stick it into a program that has a computerized either bomb blast event put in or an earthquake put in, and then it sees what that equipment does during that piece of either earthquake or bomb blast, right? The calculations performed, they are to size the restraints for the anchorage, right? Based on code-specific information such as the U.S. Geological Survey for earthquakes in the United States, right? Static analysis does not guarantee the function of the equipment, but only that it will be still bolted down in place. Come on in. Still be bolted down in place after the event, right? And that's what many areas of the United States, that's what they're looking for. Make sure the equipment's in place, right? It's what we like to call in the United States trying to figure the word is just trying to save human lives. In other words, it's a life safety issue. It's not trying to save the equipment. It's trying to save the guy who's changing the filters. That day, he happens to be in there changing the filters when either a blast or an earthquake happens, that the equipment doesn't fall on him and kill him. Or the pipe that's running through up here, or this ductwork that's bringing in fresh air, doesn't come down and land on my head and kill me. All right, most of it is just life safety, trying to make sure it stays in place so that it doesn't harm anybody and doesn't block egress, all right, out of the building. So this is basically how you would do a dynamic analysis and a static analysis. You would start off with a piece of equipment, like I said, a pump. You figure out where its center of gravity is, you've got a height, you've got some vibration isolators, which happen to also be a seismic snubber in this case, and you run through a set of calculations to go ahead and say, okay, I figured this out, and it turns out that there's X amount of tension on this one, there's X amount of force on this one, but then you have to do the same calculation twice, all right? Because that gives you, that first calculation gives you the information at the top of the bolt. Well, then you have to then transfer that bolt down to the bottom, which is now going to be anchored into the structure below. All right, so you end up having basically two sets of calcs, and they somewhat look like this. They sort of look like this, where you figure out the actual tension on a bolt first, and then the actual shear, and then you divide them to do the same calculation twice over the vibration isolator to get down to figure out what your actual anchorage needs to be. All right, so if you're in a very low area, you might need a 12 or 13 millimeter bolt. If it happens to be in a very big area where there's going to be either a better chance of a bomb blast or a better chance of a seismic event, maybe this is a 16 millimeter bolt or a 20 millimeter bolt, something like that. Okay? But like I said, this is one of the areas that needs enforcement. This is where people go, I don't want to drill that big concrete anchor in. I'm going to put a small one in. And that's why you need to have some field enforcement to make sure you get the bolt that's required to do the job. Okay? So then, in the United States and here in Europe, all right, there is a system for figuring out when you have tension and shear on pieces of equipment, now on bolts, how you go ahead and you figure out the actual allowable load of that bolt, okay? And basically, when it's all said and done, these two equations need to be less than 1 or equal to 1, and that's it. So as long as you're below 1, that means your anchorage is going to hold up fine during the event that you've just designed it for. A few of the things that have failed in the past are anchor bolts. All right, I talk about anchor bolts a lot because every piece of equipment is either held in place by an anchor bolt or it's held in place by threaded rod. Okay. After the Northridge earthquake of 1994, I inspected about 40 buildings in California. And one of the things I found was that anchor bolts just sheared off, okay? And it had never been seen before, or it had never been cataloged that this has been an occurrence that happened quite often. So what we did is we kind of figured out what was going on was you have a piece of equipment, you've got a hole in the equipment, and the contractor puts in the correct size bolt, and he tries to center it as best he can, which is fine. But then the earthquake or the event happens, all right? So this thing starts moving back and forth. The equipment tries to stay in place, the floor starts moving back and forth. And what you end up is one side hits the side here, then it moves the other way, and it hits the side here, and then it just keeps going back and forth to the point where you shear off the bolt, you fatigue the bolt. Now I'm sure every child at one point in his life has taken a little piece of steel and you've done this. So all of a sudden, oh, you got two little pieces of steel. That's exactly what happens here. That's fatiguing. You just do this and all of a sudden you've fatigued the steel to the point where it breaks into two. Well, that's exactly what happens with bolts. They just fatigued off because during most of seismic events, there could be 300-400 cycles that the bolt gets going through, being hit. I've got another photograph that I'll show you in a minute that kind of shows you how much a pipe got strapped by, got scratched by the steel work holding it up. Okay? So what happens is, if that bolt fails, all right, you have nothing holding it down and it tips over. All right? And that's what you don't want to happen. Okay? So in the failures, you have, if you had equipment that had no seismic restraints on, just let's say a spring isolator sitting up there, right? Figure 1, it's ready. Figure 2, the ground starts moving. Figure 3, everything's moving in all directions, and somewhere along figure 4, the equipment's going to fall over. So this is why you need to have some kind of restraint system built into anything that you're going to use if you're going to have vibration isolators, or even if you're not going to have vibration, you still need some kind of anchorage system to hold it in place. Okay? A dynamic analysis is performed using a specific shock input. And this could be a certain bomb blast if you've got a bomb blast envelope, and I'll show you one in a moment, or it could be an earthquake envelope, and they're slightly different. Okay? The dynamic analysis uses finite and element analysis to determine the forces, the accelerations, and the displacements of the equipment of this system. So in other words, if you take that same pump that I showed you before, and you ran a dynamic analysis on it, it's going to come out and tell you what the forces are at the top of that restraint, and then we would then do a stack analysis to bring it down to the anchor bolts below it. All right. The supporting system can be redesigned based on the output of this analysis to ensure survivability. That's what ends up happening. Somebody gives you an answer, they start off with, okay, I'm going to take this pump and I've decided I'm going to do this, this, and this to it. And you run the analysis and you go, nope, you're not going to do this. You're going to need to do this, this, and this to make it survive, okay? And then you end up working back and forth until everybody's happy with what ends up happening. Because what ends up happening quite often is you need more real estate, you need more space. You need to put a bigger snubber in. You need more space to put anchorage in. And in mechanical rooms, that can be tough to get, right? When I started working almost 40 years ago, mechanical rooms were big, and they had all the room in the world. Well, now they're trying to fit them into the smallest space you can figure, all right? This, because every square inch is retailable. Got to be able to be rentable, all right? So basically, they're now shoehorning equipment in. All right, we have jobs where we used to put 4 pumps across 20 feet. 4 pumps now got to fit in 5 feet. Right? And what you end up doing is turn one this way, one that way, one this, you know, whatever you can to get them into the area that they have. So this is what a mathematical model would look like, all right, for a dynamic analysis. I would take this pump, this fan system here, and it's got different center of gravities for all the different spots. All right, there's a center of gravity of the fan, of the motor, one of the fan, one of the isolation inertia block underneath it, one of the section holding up the motor, and so on and so forth. You take all these different components and you add them in at the different elevations that they are in, right? And this dynamic analysis then goes ahead and runs and spits out answers and tells you what the loads are right at the top here, right? And then you then have to figure out what we're going to do to restrain that system and hold it in place. Okay, so here's a typical earthquake input. Okay, so what you would look at is, all right, you got 0.2 G curves and 0.5 curves. All right, it's usually what people end up using, right? And it runs across like this, right? And what they'll do is they say, okay, we're going to start with a system acceleration based on an analysis somebody has done in the past. They say, all right, we're going to start with 0.4. We run out to there, and then it comes down to where the system displacement is. And then from the system displacement, we then figure out what we need in the way of a spring rate to move that load down to the load that we can go ahead and work on. Okay, this is a typical bomb blast. All right, this is different. All right, there's an envelope, and they'll give you an envelope. They'll say, okay, this is your envelope. Okay, And then they might even give you a specific spot within that envelope that they want you to design everything to, all right? These are the kinds of stuff that you do with a lot of military work. And it's kind of hit and miss as to getting jobs for things like this, but the military in the US and a lot of the US government work, they do a lot of this work, and I'm sure you guys do also. You just don't know about it. You know, nobody really knows that the government does a lot of this stuff, okay? So here's a basic output of one of the dynamic analysis, right? So in this one, we had a condenser, a cooler, and a motor component here, right? And what we ended up, it came out was, all right, maximum forces in the X, Y, and Z direction, maximum displacement in the X, Y, and Z direction. And those are the things that you take a look at and you say, okay, well, I've got 3/8 of an inch. I've got basically the 3/8, about 10 millimeters of movement here, okay? So I have to now design a system that can handle that 10 millimeters of movement without shearing off, right? So basically some kind of snubber that has rubber inside that can handle that 10 millimeters of movement is what you want, all right? Because otherwise you're going to start shearing bolts off, right? So what you're basically going to be doing is you're going to keep designing these until you get to a number that you're in this kind of neighborhood, all right? Otherwise you're looking at having very, very thick rubber, and it becomes more expensive to do it, okay? So there are different degrees of protection when it comes to a bomb blast, all right? We can protect just a single piece of equipment. You've got a stand-up fan over here, all right? It can have vibration isolators or seismic snubbers built into it, right down to the structure. We can do it that way, okay? We can have multiple pieces of equipment on a floating floor, all right? Where they take that equipment, everything is bolted to this floor we'll say we're standing on, but then that floor has got vibration isolators and seismic restraints built into it, so it stays in place and does what needs to be done. It moves it moves so we don't shear off bolts and so on, okay? And then there is a building within a building process, all right, where we can take a building and we can take everything that you need to put into that building, and that can just go into one particular little mini building within a building, and then put the restraint systems as needed around it, whereas this would take most of the shock from either a bomb blast or from an earthquake, and the rest of it would just bounce around inside, okay? So here's what we would do for piping systems, all right? For a typical pipe, all right, for either bomb blast or for seismic, it's done the same way, right? We put some cables on it, right? Hold it, right? Basically done every 20 feet, somewhere's up to 40 feet, depending on where, all right, and the seismic loads that are applied, all right? There's other way of doing it, and I don't think we have that on here. No. Is you do it with a rigid brace, where you would have, this is cables, okay? Or you could do it with a rigid brace with a steel frame in, all right? So just one steel part would come off, one or the other, all right? One of the problems that you have with a system such as this is you're not holding on to the pipe itself, you're holding on to the clevis hanger, all right? So what ends up happening is in a transverse location such as I got shown here, it works perfectly fine. But when you get to a longitudinal location so that the pipe doesn't go in and out of the clevis, you have to actually attach to the pipe itself, okay? And what happens is if you don't do this, it just slides in the pipe. It'll just slide in that. If you were to hold this without having the pipe actually be attached to it, it would just slide within the clevis and not do you any good. It would still move around in the one direction, okay? And if you had trapeze piping, it's the same thing. You would put, all right, some steelwork underneath, all right? And then the only thing you would do is you would need to bolt the pipe down to the steelwork to make sure it stays where it's supposed to be. Now this isn't done at every single location that you have for support. It's done every 10 meters, every 15 meters. All right, so it might be your every third or fourth support would get done with this. So this is one of the photographs I wanted to show you. So during the earthquake, this is the insulation. It had an insulation shield, which is a piece of sheet metal. Okay. Well, as it started to move, it fell out. Okay. And then all of these here are scratch marks on the bottom of the pipe from that steel work. All right. So that's how much this thing moved back and forth and scratched the bottom of this pipe. All right. It ended up back almost exactly where it started from. Right? The pipe ended up basically back in the center where it started. Okay, this pipe didn't end up where it started again. Okay, so here you had a pipe moving back and forth. Now this is the clevis where it ended up. That's where it started. Okay, that's 800,000 millimeters away from where it started. Right, fairly large amount of movements during some of these events. Okay. This one happened to have had a vibration isolated up at the top. So what happens is when you have that is it's actually very flexible and allows it to move very much. If this had been a threaded rod right up into the ceiling, it's more of a possibility it would have fatigued itself and broke off. Here's another problem we found with the actual connections of holding up the pipe. So that's a standard pipe clevis that you can buy anywhere in the world, okay? And there are no such things as heavy-duty pipe clamps or anything like that. This is basically what every HVAC contractor uses in the world, okay? So during the earthquake, this jumped up and it hit the center of this bolt, okay? Bent the bolt up. Then the whole system came back down, and this side of the clevis just slid down to the lowest point possible. So now you've got to replace that, okay? There's a bunch of real easy fixes for that. And one of them is a piece of pipe. When the contractor is installing this, if he had put a piece of pipe on there that's basically just bigger than whatever the inside diameter, bigger than whatever the OD of that bolt is, he could have saved that, because you never would have bent both the bolt and a piece of pipe, okay? And that is going to cost the contractor a couple of pennies, okay? But now he's got to go back, he's got to support the pipe, he's got to take this apart, he's got to put a new one in, okay? Hopefully this time with some pipe on there or some other form of bracing it. Okay. So ductwork, just like piping, okay, can be done with bracing. Here I show steel bracing this time, all right? So that's just one-sided, okay? Whereas the cable, you had two cables going off the side because cables only work in tension, they don't work in compression. So steel works in both compression and in tension, okay? But one of the big problems with ductwork is such light gauge. You cannot just bolt onto a piece of ductwork. It's too light. You go to pull it apart, it'll just rip the steel out, right? So you end up having to put steel on top and bottom to try and keep this in place as a rectangle as it's starting. So that way your surfaces might still be able to be working. So you've got steel above and below, and we've got sheet metal screws holding it in. So this stays as one rigid rectangle now. And then you have your braces off of the steel work, right? Someplace obviously that can hold on to the steel, hold on to the braces and transfer forces. Okay. At ASHRAE, when we started our technical committee on bracing many, many years ago, there were certain companies and certain industries that fought us about having a bracing system, right? The duct industry was like, there's no reason to brace duct. It's too light, it's not gonna go anywhere, okay? Well, this is an extreme though, all right? Look at the length of these straps holding that, what held up ductwork at one point, okay? Well, now it's down there, okay? Ductwork, just like piping, still has enough weight to it that you can get momentum moving this thing back and forth, and it'll fall out. It'll come down, all right? And again, all we're trying to do is save it so it doesn't fall out and hit me in the head, all right? So you go to equipment, and then equipment goes, okay, well, I've got a fan up in the ceiling here and so on and so forth. Okay, well, same thing. You still need to brace it. Otherwise, it's going to come down, right? If in the building codes in the United States, if your fan is small enough under a certain weight and it's rigidly attached to the ductwork and that ductwork is braced, then you don't need to do the fan itself as long as it's part of the system, right? And then every 4 years, they change that. You know, they move it to, okay, this year it's 50 pounds. Oh, next year it's 75 pounds. And then it's 50 pounds with these new caveats. You know, it just drives you crazy. They keep changing the code on us. So one of the big problems with a lot of equipment was anchorage, all right? Here you have pieces of equipment, right? They were bolted into this plinth here, didn't do so well, all right? And these had seismic restraints on them, right? But they weren't designed correctly, and the actual spring holder was cast iron. And cast iron and any kind of movement don't go well at all. And so basically the cast iron broke up into a million pieces, and the springs went flying everywhere. Now, have you ever seen in the movies springs flying across the room? That's exactly what happens, all right? We have our own test lab, and we do a lot of springs, and we have 1-inch thick plexiglass in front of the test machines because we've had springs pop out and fly across, okay? So basically what happens is these didn't work so well. Like there was an ankle bolt, you can probably see right there, and it broke the casting off, okay? So this is what happens if you don't have a plinth that is designed correctly, all right? So the action of a plinth is to, in most mechanical rooms, it's just to raise the equipment so if there's a leak somewhere, it's not sitting in water. That's the basic premise, okay? But it's also your structural attachment to the rest of the building, all right? So what you have is, in this case, you had about 200 millimeters of concrete, but you wasn't attached to anything, and it wasn't reinforced. So basically what you made was this big plaster inertia block, and then you bolted the equipment onto it, right? It had seismic snuggers. They're way out there now. Not doing any good though, okay? So this hospital, this happened to be the 3rd floor of a hospital. This hospital had seismograph equipment on that floor. It saw a 1.1 vertical G input. So the idea is we think when the input went up, it actually threw the equipment up in the air. I mean, you know, maybe this much, you know, whatever it is. But it lifted it off the ground, came back down, and it shattered like a pane of glass. And that's what it ended up looking like, right? Because there was no reinforcing, all right, no attachment, no doweling into the structural slab. So that really isn't a load path that is complete to move all the forces down to the structural slab of the building. One of the other problems also is all of these connections here, they all ripped out, right? Those are where flex connectors could have been, all right, been put there and saved this, all right, and moved with it and not broke. So what happens when all this water breaks? All these connections break on all these chillers. Where's that water go? Down, okay? So what does it do? Takes out that ceiling, takes out that wall, takes out the floor, takes out anything in this room. It's destroyed. And then it goes to the next floor below. And it keeps doing it until there's no more floors to go to. And it ends up in the basement where, all right, they pump it out eventually, right? So a lot of hospitals in California ended up after this just demolishing the buildings. They weren't worth repairing at that point, all right? And they start over, right? In America, new baseball and football stadiums. We'll make a new one in the parking lot of the old one, and then we knock down the old one, and that becomes the parking lot for the new one. But for those 3 years, you got no parking anywhere. You know, you've got to You got to take the tube in, otherwise you're not going to find any place to park. Housekeeping pads are plinths in large parts of the world are basically overlooked, and probably one of the most important pieces of equipment in a mechanical room, because they attach equipment to the structure itself. Right? They need to be reinforced, and they need to be attached to a structural slab. Okay, so here's another one where photograph of, there was a seismic restraint, a big inertia block on a housekeeping pad, right? But they didn't have any rebar reinforcing in it. So what happened is, as it started moving back and forth, the equipment, the two bolts holding in the seismic restraint, just knocked the edge of the housekeeping pad off. Right? Here are the two bolts. They're still in place. They used to be right there. They just knocked the edge out because there was no reinforcing in it. All right? In the United States, the code now calls for a minimum of 1 bar past that. So there's always at least 1 steel bar in place to hold it in, so it doesn't happen again. So this is typically what, wow. Well, if you could see that, it's basically a plinth with reinforcing and dowels in it. All right, that is basically what you're looking to do. Floor-mounted equipment needs to have some kind of system to hold it in place. All right. This is one of the photographs I show people because you need to think ahead of what could happen. All right. So here you've got a heat exchanger, and you've broken off the end cap because it used to be here and now it's over there. So what do you have now? You got 500 kilos of scrap metal. That's all you got. It's useless. You're not going to be able to find a new end cap for this. Okay. And the chances of finding somebody who's got a new one in town are very slim. So you're going to have to wait for the next production run. It could be 6 months. What if this was a hospital that had to keep running and needed that heat exchanger in place? Okay? Putting a flex connector in there could help solve the problem one of 2 ways. The first way is flex connector might move everything, allow everything to move around enough that it survives. Hey, great. All right? The second is, well, maybe it tears a little and leaks a little bit. Great. But the equipment's still there and it's still okay. You can replace a flex connector in a minute, or you can take the flex connector out and you can put a spool piece. That's what we call it in the States. It's a piece of pipe with a flange on each end that's the same dimension as that flex connector would have been. You stick it in there and you're back up and running, and you can replace the flex connector later on when you can get hold of it. But you can get back up and running, and that's the main thing, right? Try not to lose the equipment, because that is just scrap metal now. There's nothing you can do with it, right? Unless you happen to have 2 of them and you broke the other casting of the other one and you can swap castings out. That's about it. Okay. So if you use flex connectors, they're able to handle axial compression, axial elongation, transverse movement, and angular movement. Come on in.
Sorry, I was looking for you in a different room. Sorry.
Most rubber connectors do not offer movement capabilities to handle bomb blast requirements, but they can also be designed to handle that, or combinations of them put together to get to the movements that you might see in a bomb blast protection job. Right? Generally, most of them can handle about 1 inch of movement. Okay, 25 mils of movement. Right? And then you go to flex connectors that have braided stainless steel in them, and they can end up with much bigger movements on them. Right? But you also need more space to put them in. All right? All right? If you were to do a standard loop on for a steam pipe or something like that, your loop could be tremendous. All right? Newer styles made by many companies where they make them in different V styles and U styles or so on, right, are able to take up that same amount of movement in a much smaller space. All right? And the chances of you tearing one of these out and having to replace it, very low. But again, right, they have capabilities of, up to 100 mils of movement, but They take up more space. Okay? The connections, all right? In all of this, be it bomb blast or be it earthquake, there's always a problem with connections, all right? Now here, whoever had originally designed the steelwork for this thought he had done a great job. I mean, he built this big concrete pier. He's got big bolts on it. He's got a huge I-beam. Great. Sounds like it's a great job. Except for one thing. This angle, which is bolted on with large bolts to the cross beam, was only tack welded. Okay? A couple little tacks of weld, and that was all. And it just came apart and down came apart. The only thing holding the system together is a vibration isolator, because that did not fail. It's still there working. It's doing what it's supposed to do, hold everything together. Okay? So in connections, you have a few different styles. You have welding, steel bolts, lag bolts into wood beams, and post-installed anchors into concrete. All right? Welding, you don't get much of a chance to weld things onto the building structure anymore, because by the time the mechanical HVAC people get there, the building has already been built, the steel columns have already got the fireproofing on, and there's no building official who's going to let me scrape that off so I can weld onto it, okay? But sometimes if you're in an older building, you might be able to get to it, right? Steel bolts, right? Well, chances of bolting to that same column, again, are fairly slim because it's got your fireproofing on it, right? Many parts of the world still do a lot with big wood beams, all right? Here in old parts of London, I was in a pub last night that was built in the 14 or 1500s, okay? Everything in that thing was wood, okay? And basically, you just have to design lag bolts to fit into the wood, all right? But 90% of your attachments are going to be into concrete structures of some form, be it a deck with concrete or just a concrete slab itself. Right? So post-installed anchors become the main way to go. And there are many kinds of post-installed anchors. And there's a lot of junk ones out there, and there's a lot of good ones. Right? You have wedge anchors, right? You have concrete anchors, you have chemical anchors, or otherwise known as adhesive anchors, right? You have what are known in the United States as drop-in anchors, which basically look like a little tube of steel and it's threaded, okay? Each of those has their good and bad parts, right? In the United States and in most of Europe, there is a code that says you have to have a certain amount of testing to be used for one of these types of jobs, all right? Do I have it in here? Yes, I did, good. All right. So basically, they include wedge, undercut, and adhesive anchors. Undercuts are probably the best anchor, right? So what you do with an undercut is you drill a hole, and then you put another drill bit in that flares out the hole, and then the anchor goes in and flares out, and you got a mechanical anchor that just can't come out of that concrete. You would literally take a chunk of concrete like this out when it comes out, okay? But they're also the most expensive and the hardest ones to install into concrete. Okay, they have to be tested through European Technical Guide E-Tag 001, or in the United States, ACI, which is the American Concrete Institute 355.2, all right, for seismic capabilities. And that is not a little test. That is somewhere in the neighborhood of 35 different tests. And then when there are 35 tests, there are different parameters on that. You do the same test in lightweight concrete, hard rock concrete, pumice concrete, in oversized holes, in undersized holes, in wet holes, in holes that are freezing, in holes that are hot, and then the last, holes that are cracked, and they cycle the crack. What they do is they actually take and drill, like if they're going to pull on this anchor right here, about 300 millimeters away, they'll drill another hole, and then they'll put an airbag in there, and they'll cycle, they'll make a crack go from there to there, and then they'll cycle that crack, and then pull on the anchor while they're cycling the crack to see how it does in cracked concrete. So if you look at a lot of American anchor bolts, they'll say, certified for cracked concrete. That's why, because they passed the concrete crack test. And it takes forever. It takes, for one standard anchor bolt, even in one size, it could take close to 2 years to do all the testing required. Because you're only allowed to test in a slab that is X amount of days old, up to a certain amount of days old. So it's not like the test lab can make 500 test slabs and leave them on the side. He's got to be making slabs almost every day to continue out on that cycle. So it takes him quite a while to do everything. Okay? This is one of our non-compliant restraints, okay? In ASHRAE, I chair the technical committee for junk like this, all right? And basically what it is we have put together, ASHRAE has a standard, I'll show you a picture of the standard in a moment, for testing of restraints for both bomb blast, seismic, and wind, all right? That's so that people don't sell junk like this and say, it can handle all the forces you've got. Well, prove it to me. Show me the testing, okay? These were, as you can see, they were actually what we call high deflection. This was probably 75 to 100 millimeter deflection spring, which they're big, physically big, okay? Now what they have is, they got this little thin 6 millimeter plate, which as you can see, bent all over the place, okay? They got big, beautiful channels, big, strong, beefy channels, but they're connected to this little 6 millimeter plate, all right? They got one hole on that side for anchorage and one hole on the other side for anchorage. Basically no anchorage because the plate isn't wide enough, and they put one anchor in the very center. So it just teeter-totters off that until the point where it breaks off and everything goes, right? And like I said before, you don't want to be around when one of those goes flying, okay? It could kill you instantly if it hits you, all right? So this is one of the things that ASHRAE is very intent on changing, is people selling stuff like this. Okay, so this is the ASHRAE standard, all right? Method of testing for seismic restraints, for seismic and wind restraints, all right? Came out last year. That's actually the second edition. The first edition was in 2008, all right? And then in 2015, the building codes in the United States changed, and they wanted to see additional fatigue testing. So we've gone to fatigue testing, and now it's an ASCE standard, which means that it's able to go into the building code, and we're expecting this to be part of the United States building code in the next 6 to 8 years. It takes a long time to get in the building code in the United States. Okay. Okay. Well, this is where I was going to show you a shaker table. All right, which is, this is how I was saying before, how you can find out the fragility level of equipment. Well, in the United States now, a building official has the right to ask you to say, that chiller is supposed to go into my building that you're building. Prove to me it can handle the seismic capabilities, right? And so the shaker table test is a shaker table, and what it does is it moves on a pre-planned earthquake. It's actually the San Bernardino earthquake of 1972 is what they moved it on, all right? And basically, this thing moves like all over the place. Well, let's see, maybe I'm lucky it'll work in this view. Cannot play media, okay? Yeah, because it moves quite a lot, all right? This happens to be on vibration isolated, so it would move more than it would if it was just bolted down hard, all right? Basically, this was an ASHRAE shaker table testing. ASHRAE has done, in the past 15 years, has spent about $750,000 on testing of different things in seismic and wind. We're about to come out with a brand new set of wind information that will end up in the building code in 4 years because they're waiting for it, okay? ASHRAE has decided they want to do a lot of this stuff to help out in the building code. So what we did is, as ASHRAE, we tested a lot of this equipment, and what we did is what we were trying to find out was what was the best seismic restraint that you could use, all right? And most seismic restraints are basically some steel framework and there's some rubber. well, how thick should the rubber be? How hard should the rubber be? And what kind of air gap? Because you have to have in a seismic restraint, you have to have some kind of air gap for the vibration isolation to work on its day-to-day, everyday use. And then it locks itself out when the earthquake comes. So you have to have some kind of air gap. So we went through every available possibility of hardness of rubber, thickness of material, and air gaps in every combination possible, all right, to come up with what is now the ASHRAE listed standard, all right? And basically, it is a 20 millimeter thick rubber, all right, with a 6 millimeter or less air gap is what it came out in a medium soft hard rubber is what it came out as, all right? This was done at the University of Buffalo in Buffalo, New York, all right? The University of Buffalo has got the 2 biggest shaker tables in the United States. And everybody goes, why would they be in Buffalo and not out in California somewhere? Well, the reason is because they're not in California, they got it, right? About 20 years ago, the US government decided they wanted to put a couple more shaker tables at the place, okay? So they went out for bids. And all the universities on the West Coast in California, yep, we want to do it, here's our plan, so on and so forth. And the government went, no, let's go out for bid again. And then they contacted universities on the East Coast of the United States where basically is no earthquakes. They said, we think you guys should see about bidding. And they're like, why? We don't have earthquakes. That's the reason. The government was sick and tired of fixing these and paying to have these fixed every time there was an earthquake. And when there were an earthquake, they'd be down for 6-8 months until they got repaired. So what they wanted to do is put it somewhere where there weren't going to be any problems with it, and it runs all the time, right? So what they have is 2 of the biggest, right? This is one, and then about 15 meters to the right is another one the same size. They can be linked together to be the biggest in the world, okay? Which it was at the time. And then the University of San Diego built a bigger one, but they built it outside. And the University of San Diego built one where outside that they built a 4-story building on it. All right, complete 4-story building, and they shook that whole building, and in it they tested everything out. All right, they tested rigid braces for piping on one floor. Another floor they did cable bracing. Right, they had a cooling tower up on a roof. They had pumps on the first floor. They had everything, both mechanically, architecturally, that they needed in a building. So it was like a complete real building, and then they tested it. Okay. Did all this testing, great, everything worked out pretty much as they had planned. They found a couple things that wow, that was different, they didn't plan on. And then the National Fire Protection Agency, NFPA, our association, sorry, the plan was that it was called the shake and bake. First we shake it to death, and then NFPA came and burned it down to test all the sprinkler systems after they had gone through the earthquake. And they actually did very well, all right? And then the US government ran out of money, and they never printed the test reports. So we all know about it because we were all there. I witnessed it because I designed all the seismic restraints on the inside of the building, but we have no proof. And I think that's basically it. Yeah, that's it. Any questions?
Thanks, Jim.
If not, let's go get a drink.
Can I ask you one?
I would love it.
You talked about field enforcement being the big issue, because obviously you're specifying these systems. There's quite a lot, presumably there's quite a lot of extra cost involved in putting the extra restraints in and getting the rigidity into the system and so on. How would you go about enforcing it in the field if people are going to try and cut corners? I guess because the additional cost is a temptation for them to. And you talked about the junk that does get installed, so people think they're getting a protected system, but they're not. How can you take all that data and make sure it's enforced and installed properly?
By letting people know about talks like this. All right, we do talks like this to all the building officials to let them know that there is availability of test reports. All right, they can ask for them. All right, through ASHRAE, we have lectures all the time. All right, like I said, ASHRAE sends me all over the world to give lectures such as this. All right, so we're putting it out. All right, building officials are putting it out also. We get quite a lot of requests from building officials around the country. Can I have a few of these slides that I can show to people? Sure, no problem, you know. But basically, the enforcement comes down to the owner has to hire somebody to basically take a look at things. All right, we have in the United States something called the special inspector, right? And it's mainly used in California hospitals, all right? And that is somebody hired by the owner, not the contractor, not the vendor such as myself or anything, but he's hired by the building owner. And his job is to oversee the bolts going in, right? And testing of the bolts. When you hire a special inspector, what he'll do is he'll go out and test some bolts that you put in. He'll just randomly say, I'm going to test that bolt that you put in for that chiller right there. And they bring in equipment and they pull down and they get it to a certain point. Okay, it hasn't pulled out, fine, and they leave it. Because you know, once it comes out, there's nothing you can do with it. So they do test them to see if they're installed correctly. Yes, sir.
Are there any plans for ASHRAE become nationalized?
Are there any plans in the United States for ASHRAE to become nationalized? No. All right, ASHRAE is the state of California. It's only for hospitals, but in many parts of the country, people will use that because they're the only ones that have really gone a step ahead of everybody else and said, hey, let's do testing, let's do this, let's do things like that. Let's have a series of pre-approval system where you can go ahead and say, okay, this seismic restraint is pre-approved for X amount of load, okay? So most companies in the United States have got ASHRAE approval on many of their products, right? I don't know of many outside the United States that have gotten any. There is a couple companies here in London that I know are in the process of doing it. So eventually you'll have somebody, I think, around here. No, but I can't talk commercialism here. Any other questions?
I think we've got to wrap it there because you've paid for all this magnificent food and stuff. We don't want to, and then we'll get thrown out at 8, don't we? If you want, I mean, Jim's going to be around for a bit. We're going to have some drinks and some refreshments out there. So please stick around until we get thrown out at 8. Thank you very much. I think a big round of applause for that fantastic.